our boundary layer looks something like this. We have our coordinate system set up where we have x and y. And then we have our boundary layer delta. So we want to know what's the velocity profile for the system, and then also what is the shear force. And so where we left off was we had our Navier-Stokes equation in terms of our streamline function, which was a function of both x and y. Alright, and then I introduced this idea of a modified stream function, particularly because our streamline function here is both a function of x and y. And it's very difficult to try to solve this differential equation, so we introduced the Basseau's solution. We have our modified stream function, which is equal to our stream function over the square root of our velocity times our kinematic viscosity times our variable x. And then we use a nu being a combination of variables, which is y times the square root of u over kinematic viscosity times our distance x. And so what we have to do is solve for these terms or solve for these individual sort of expressions in terms of our modified stream function and our one independent variable nu. So I start off with looking at the partial of stream function with respect to y. And so what I first did was go ahead and write our modified stream function and multiplying each side by that numerator. So we had the square root of u times the kinematic viscosity times distance times modified stream function is equal to the stream function. We could go ahead and take the derivative of both sides with respect to y. This is just a constant, so that's left alone. Sorry, ran out of room. So now we have this relationship. However, we still have y in here, so we need to change this out for a nu. So in the same way, I could go ahead and multiply each side by the denominator. And then take the derivative of both sides. This is, once again, just a constant. So I get d nu dy. So with that, I could go ahead and take this relationship and plug it in for my terms or a dy. So this is just a transformation. So when I go ahead and do that, I still get the square root of velocity times kinematic viscosity. Now over that substitution in for dy, which is going to be our kinematic viscosity times x over u. And this is the partial of our modified stream function, d nu is equal to the partial derivative of our stream function with respect to y. So when we do this, this term cancels out, and then we're left with just u times the derivative of our modified stream function with respect to nu is equal to our partial stream function with respect to y. And also to note that the partial of the stream function with respect to y is also equal to ux, which is essentially what we're trying to solve for. So once I do that for each one of my terms of my Navier-Stokes equation, it's in terms of our stream function, so I have to do that same substitution for my modified stream function and also my nu for x and y. And once I do that, I get a new differential equation, so I get the third derivative of my modified stream function with respect d nu plus 1/2 my modified stream function times the second derivative of my modified stream function with respect to nu is equal to 0. So there's my differential equation. Similarly, I have to change my boundary conditions so they are also in terms of my modified stream function and nu. So for the case where y is equal to 0, nu is going to be equal to 0. And then in this case, my modified stream function and the derivative of my modified stream function are also going to be equal to 0. And then in the case where I have y is equal to infinity, far away from the plate, nu is going to be equal to infinity. The derivative of derivative of my modified stream function is going to be equal to 1. So now I have this information, I could go ahead and solve for this differential. Unfortunately, there's no analytical solution to this differential equation, so it's only a numeric solution. So in that regard, we'll have to use like Mathematica or MATLAB or some kind of computer software to numerically solve this. And once you have that numerical solution, then we could go ahead and look at how that varies. And for example, we have to take a look at the derivative of that function with respect to nu to get our velocity profile in the x direction. So that explains that's the first step of our problem. However, if we want to continue to kind of examine this boundary layer, and in particular look at it as a function of x, and denoting that we should have our velocity vectors look something along these lines. And for this case, where y is equal to this boundary layer, we say that u of x should be pretty much the same as our velocity that's being flowed over our plate. So I'm going to say that my flow in the x direction is 99% of that of my velocity. And so in that case, I say u of x is equal to 0.99u, and remembering that this is equal to the partial of psi respect to y, which is then also equal to u times my modified stream function derivative, nu. And so when I do this, these two terms cancel out. So the case where essentially my derivative of my modified stream function is close to 1 is a case where I have my boundary layer. So the question is, when does nu equal this? And when I do our numerical solution, we find that nu is approximately equal to 5 when the derivative of our modified stream function is equal to 0.99. So with that, we could go ahead and take our value for nu, which are a combination of variables. So in this case, y times the square root of u over kinematic velocity times distance, x. Go ahead and plug our relationship in. So here it's going to be 5 is equal to delta, which is our y value, u over kinematic velocity times our distance, x. So we could go ahead and solve for delta. In this case, is going to be equal to 5 times the square root of kinematic viscosity times distance over u. Alright, so with that, we could go ahead and see what that looks like. So as that's saying is that our thickness of our boundary layer is proportional to the square root of x. also proportional to 1 over the square root of u. Alright. So higher velocities are going to then allow this to essentially get flattened out more flat compared to lower ones where it's going to form more quickly. Okay, great. So this is the first. Alright, now the second part is I want to know what is the shear force of the system. So remember, pulling back from our shear stress relationship, so that shear stress flows into x, y. It's going to be to our viscosity as a partial of u of x with respect to y, and it's going to be evaluated at the surfaces. Remembering that it looks like this, and then we want to know what is actually this shear force acting on this plate. So that we have to determine evaluate what this derivative is. So remembering that u of x equal to the partial of our stream function with respect to y is equal to velocity times derivative of a modified stream function with respect to nu. And so I could go ahead and take this relationship and then plug it into here. So in that case, if I look at the partial of u of x with respect to y, this is going to be equal to the partial of y times this relationship right here. So this is going to be u, the derivative of a modified stream function with respect to nu. And what I'm going to do here is I'm going to transformation between nu and y. So when we do that, essentially, you kind of get about taking the partial of nu to the top and bottom. So your bottom part, here's inside it, the n. And then finally, this is going to be the top part, d nu, and the dy, which is just being pulled out. And so when I go ahead and do that, essentially, u could get factored out because it's a constant. It's now because the second derivative of my modified stream function with respect to nu. And then I have this relationship d nu dy. And I've already established that relationship previously. And so this is just equal to the square root of u over kinematic velocity times density. Times distance. So therefore, our partial of u of x with respect to y is going to equal u times u times the square root of u over kinematic viscosity times distance times second derivative of a modified stream function with respect to nu. So now that I have this relationship for my partial derivative of u of x, I could go ahead and play it back in my shear stress terms. And when I do that, my shear stress is going to be equal to u times u times the square root of u over my kinematic viscosity times distance, evaluating the second derivative of a modified stream function to nu, and in the case where y is equal to 0, nu equal to 0. Right. So once again, this is only going to be solvable by evaluating our numerical solution. And when I evaluate this numerically, it is equal to 0.33. So therefore, my shear stress is equal to 332 times my viscosity is u square root of u over kinetic viscosity x times the second derivative of modified function with respect to nu. So things to note is that my shear stress increases with viscosity, it increases with velocity, it decreases with my kinematic viscosity and my distance. So you can think about as I move further away down the plate, my shear stress becomes weaker dependent on x. And that's kind of what you expect, right? Because essentially your gradient in this direction, which is essentially your ux with respect to y, isn't changing as much. It's becoming more normalized. Alright, so with that I want to calculate my total force. So my shear force is going to be equal to um, this whole length L, integrating my shear stress over some length x, and then finally also times my width, because you could think about this as being shear stress times the area. So here's the length, and then here's my other. So this is the width of my plate. Alright, so when I do that, I'm going to factor out my W. I'm going to go ahead and plug in my relationship for shear stress and evaluate from 0 to L. And this is 0, and this is the length L. And in addition, I'm going to go ahead and factor out my x. So I factor out my x from my relationship for my shear stress. It just becomes x to the negative half power x. So I could go ahead and these are all some constants, move them in front. 0.332 W mu u times u over kinematic viscosity. And then I go ahead and evaluate I work the power divided by the power, so that's going to become positive 1/2 divided by that becomes 2. So then it becomes 2 times the square root of x, evaluated from 0 to L. Perform that evaluation. So 0.332 mu u. Do this is going to become u kinematic viscosity. This is going to be 2. This is going to be square root of L. Okay, good. Clean everything up. So 0.664 W mu u. And I'll go ahead and factor in this L. And I'm also going to break up my kinematic viscosity. So this is going to be rho L over my dynamic viscosity. So looking at this term, does this look familiar? So it looks kind of like a Reynolds number here. So I write this as square root of Reynolds number length, where Reynolds number is subscript L is velocity density length over my viscosity, where it's defined by the length of the pipe. So L is defined by the length of the plate. Okay, so finally, my shear force for my system works out to be 664 W u square root of Reynolds number length for my system. Alright, so the next thing I want to go ahead and examine is look at what is my friction factor for my system. So here, remembering our friction factor is equal to our shear stress over our kinetic energy term. The reason why I want to look at this is I want to demonstrate that you can imagine that the shear stress is a function of distance x. So therefore we have a localized friction factor. And as it increases, this shear stress term varies. It's a function of x. And so what you see here is that we have our shear stress term, which is equal to our 0.332 viscosity velocity times the square root of velocity over kinematic viscosity over distance over 1/2 rho velocity squared. And so what I could do this is the local friction factor. So it takes the example, essentially the shear stress at that location, in this case x, is the localized friction factor. Alright, so with this I could go ahead and clean this up a little bit. And in addition, I could go ahead and put these into terms of square root. So if I square them, they could go inside. Same thing with this mu. So these terms right here are going to stick around. This is still 1/2. So this is u. In this case, this becomes u squared. this rho becomes rho squared, and then something with this viscosity term up here becomes squared. If I move inside here, and then I'm going to go ahead and break up this kinematic viscosity term into density and viscosity. And then finally over x. So this helps kind of clean up some of these terms a little bit. So this cancels out, that cancels out, that rho cancels out, this viscosity term cancels out. So then go ahead and multiply my 2 on through. This becomes 0.664 times the square root of mu u density and x. And once again, if you look at this, this looks like a Reynolds number. It's actually 1 over the Reynolds number with respect to x. So here, our localized friction factor is 0.664 times 1 over the square root of x. Or if I go ahead and factor this out, we get the square root of the Reynolds number inside the denominator. And once again, it's important to note that this is defined by the local position of x. It's not necessarily a characteristic length as we normally think about our Reynolds number, but it's associated with a certain position. And similarly, you could go ahead and graph this as a function. Think about this x, and this is a friction factor. For small values of x, this term essentially gets really, really large. And so it's going to look something along the lines like this, and then it's going to decay to the square root of x power. Okay? So once again, this is a local friction factor. Now, if we really want to look at the total shear stress, or this whole system, we could, essentially do the same thing, but integrate over this whole length. Integrate over the whole length of x. So if you want to get the average value, so in this case, taking the average value of F, or friction factor, we could say that our average value of a friction factor is denoted by F. Note that this, be careful not to get this confused with the body force array. So it's going to be 1 over L, and then we integrate from 0 to L the friction factor with respect to dx. And so this is my function, my friction factor. And what I'm going to do is essentially integrate over this whole space, and then I'm going to take the average value of it. Hence the reason I'm going to divide by 1 over L. So I go ahead and go about doing this. 1 over L, so again, square root of it. Evaluate from 0 to L. Plug in this relationship that I have for the localized friction factor. This is 0.664. And I'm going to do a similar technique where I'm going to split up my constants and my position x, dx. So this is all a constant. I could go ahead and take this on through. And I could go ahead and bring this on inside as well. So mu over L squared u d. Raise the power, divide by the power, so this becomes 1/2 divide by 1/2 becomes multiplied by 2. And this becomes x to the 1/2 power. Evaluate from 0 to L. So when I do this, it's 2 times this value. So it works out to be 1.328 u L squared velocity rho, and then this is square root of L. So one of these terms cancel out with that. So one left is 0.328. Once again, this is now a Reynolds number. Square root Reynolds number length. This is now my average friction factor. So what's nice about this is that I hope this shows that there's a relationship between my friction factor and, in addition, similar to my shear stress or shear force as well.
So this velocity solution is really only good when the Reynolds number based on x is less than 10 to the fifth, or sometimes you'll see in books 10 to the sixth. I like to use 10 to the fifth because that's a sort of more conservative estimate. But the exact number where the solution breaks down is highly dependent upon the exact conditions of the experiment. Do you have a lot of free stream disturbances, or is the velocity profile coming at the plate really truly smooth? Is the plate truly smooth, or is there roughness? So we'll just stick with the 10 to the fifth number, but it's important to realize these transition numbers where solutions break down are often not very precise. But what we'd observe then in practice would be the following. So here's our plate. And here's a location where the Reynolds number becomes equal to about 10 to the fifth. So from the leading edge up to this point, we might suspect then that the velocity solution is quite good, and in fact that's what we observe. Now let's go further along, and let's say we're out here where the Reynolds number is something like 10 to the 6th or higher. What we'd observe out here is the boundary layer is much thicker than it was, and now it's turbulent, so there's lots of fluctuations, there's lots of eddies and swirls and sort of complex structure going on here. Now if I took a little probe and we put a velocity probe at a single point and we plotted the velocity at that point as a function of time, we could describe a mean value, but we'd see lots and lots of fluctuation around that value. So it'd be kind of going up and down, up and down, up and down. It would never be steady. And if we measured an average velocity profile, what we might see is something that looks at least qualitatively like this. So here's the free stream value. We'd see maybe a slight departure from that, but not a whole lot of change over a great distance. And then a very, very rapid change right at the bottom. So our average velocity profile might look something much blunter than it did in the velocity solution, and much more dramatic transition right at the wall. And the reason it's so thin at the wall is because now we have this swirling motion, lots of eddies, which can carry high momentum fluid from the upper reaches of the boundary layer down to the plate, so it kind of blunts this thing out quite a bit. Though the region where we have a departure from the free stream velocity might be quite a bit thicker, much of that change happens over a very, very, very narrow region. Now what happens between this point and this point where we go from the velocity solution to kind of a fully turbulent one is also a little bit complicated. And again, a lot of this depends upon the details of what you observe. But in general, there's some sort of, this layer kind of grows maybe a little bit randomly. But what's observed is that first some waves start to develop. So you see some sort of wavy pattern in here. If we looked at the plate from the top, so this would be sort of a top view, looking down on the plate around this region. If we injected smoke in our flow, we might see some wavy stuff going on here. These waves are called Tolmine, I'll probably spell this wrong, Schlichting waves, named after the people who discovered them. But we see some wavy structure here. And then these waves tend to become wavy in this direction. And then they'll sort of pinch off and become these kind of triangle-y looking structures. And then what's observed are some sort of turbulent spots. So sort of random spots of turbulence, and then it just becomes totally turbulent after that. So this is kind of a basic picture. It's very complex, and the exact sort of transition here depends very sensitively on the roughness of the plate and the sort of quietness of the free stream velocity. But if you set things up very carefully in the lab, this is kind of the basic picture that you observe. So it's kind of a little bit complicated, but we have kind of the Blasius solution being good for some of the region and it being sort of wholly turbulent for the rest of the region. And we just have to remember, keep in mind, that the transition between those is not a precise thing. Describing the turbulent region is actually quite complex, but we can do it empirically because we can show by dimensional analysis quite readily that things like the thickness of this boundary layer divided by x has to be a function of the Reynolds number, and things like the coefficient of friction, which we defined as the local shear stress divided by 1/2 rho u naught squared, also has to be a function of the Reynolds number. So we know that they're functions, we just don't know what those functions are. So it turns out we can measure them. So this is purely empirical, so the functional form and the factors here, there's no magic behind them, it's just what we measure. But for turbulent, a kind of common correlation would be that delta over x is equal to 0.37 over the Reynolds number based on x to the 1/5 power. And another empirical correlation would be the coefficient of friction is 0.592 divided by the Reynolds number based on x to the 1/5 power. So these are just empirical fits to data. So what we might observe then is here's our plate. The thickness of the boundary layer delta of the leading edge grows as the square root of x. At some point we'll say here's the Reynolds number based on x equaling 10 to the 5th. And if we plot our empirical correlation for the thickness of the turbulent layer, it might look something like this. If we look at the scaling, we'd find that this grows as x to the 4/5 power, so a little bit steeper like that. And at a Reynolds number of 10 to the 5th, they wouldn't quite line up. And so what that means in reality is that something, you might follow the solution for a while, then it's going to break down, and maybe something that's not so repeatable happens, right? So if we did a different experiment with a different plate with a different roughness, we might find it looks something more like that. But at high Reynolds number or far distances down the plate, we would match this turbulent correlation. Up near the leading edge, we'd match the Blasius solution. There'd be some sort of random transition in between that would kind of depend really on the details of what's going on. So we sort of hop between these two solutions with this sudden burst in thickness of the boundary layer. If we looked at the coefficient of friction, which we define as the local shear stress divided by 1/2 rho u squared, and we plot that as a function of the Reynolds number based on x or distance down the plate, what we would find then, and we did this, let's imagine this is in log scale, so this is the log of the Reynolds number and the log of that. We would define this being a 1/2 power, this being a 1/5 power, that being the laminar Blasius solution, this being the turbulent empirical correlation, and in any given experiment, some sort of trajectory that hops from one solution to the other. It's also important to realize that while I'm drawing this structure out here, the thickness of a boundary layer is a line. In reality, it's not necessarily a line. It's a line when you average over time, but at any given instant, it might look quite different. Here's a few images from a book called Album of Fluid Motion. There's a picture of a turbulent boundary layer. We can see that at this particular instant, the structure is quite irregular. However, if we averaged over time, we'd have kind of a smooth layer where there was disturbed flow and a layer where there was turbulent flow. And just down here is a slightly different one. What we see lots of sort of structure going on here and lots of irregularity. However, if we average things over time, we get the structure and the correlations as I described just a second ago.
Boundary layer separation has one of the most profound implications for aerodynamics, which is why it's so important. Let's start by considering a boundary layer that's growing over a flat plate. The first important fact is that the change in pressure in the y direction, dp by dy, of the pressure field, which is a function of x and y, and we might as well take the origin as being the front of the plate, the change in pressure in the y direction is very, very small, so it's approximately equal to 0. Now, physically, we're just simply saying that if we look along a line at constant x, so look at this red line here, the pressure at the top there is the same as the pressure all the way along in that direction. So let's think about the velocity profile in the boundary layer. Up in the free stream we have the free stream velocity. Then in the boundary layer, the bits that have been affected by the presence of the boundary, we see that velocity tail down to 0. So the arrows, velocity vectors if you like, will look like that. So I've just copied that underneath, and in this first case here we'll say that the pressure change in the x direction dp dx is equal to 0. In other words, the pressure is constant in the x direction. Now let's imagine the same boundary layer, but in a flow where the pressure is changing in the x direction. So let's have to start with a high pressure on the upstream side and a low pressure on the downstream side. What will this look like? Well, the free stream might be slightly faster because we've gone from a high pressure to a low pressure, so we might start here. And let's think about the fluid. The fluid in the free stream has been accelerated a bit. The fluid down at the bottom, let me circle that here, which was going at a lower velocity, will also be accelerated. And so we'll find that we get a steeper velocity profile at the bottom of the boundary layer that has arisen because the pressure gradient in the x direction is the same all the way down the boundary layer, and so that really accelerates the flow at the bottom. And what I want to highlight here most of all is that at the bottom of the boundary layer we have a steeper velocity profile. And now if we consider the opposite case with a low pressure upstream going to a high pressure downstream, what are we going to find? Well, we'll find that the free stream has been slowed down a little bit, and let's follow this down. Everything in the boundary layer will have been slowed down by the same pressure gradient. So we're going to find that the boundary layer will do this. Now it's going to want to go down to negative velocities over here, but of course at the bottom it won't be able to because of momentum diffusion from the flat surface here. We need the no slip condition, in other words 0 velocity there. So the velocity does that, it bends around, and what we find is that we've got normal flow at the top and a little bit of reverse flow at the bottom, and that's the key bit. At the bottom of the boundary layer we've got a little bit of reverse flow. So what we have is what we call an adverse pressure gradient going from low pressure to high pressure, causing a little bit of reverse flow at the bottom of the boundary layer. Earlier on we looked at Couette flow and Poiseuille flow, in other words the flow between two flat plates with the top plate moving and the bottom plate stationary, with or without a pressure gradient in the flow. Let's look at the case of pure Couette flow. Remember, here we have a top plate moving at velocity v, a bottom plate that's stationary. So if we draw the velocity at the bottom, by the no slip condition it's going at velocity 0, and the velocity at the top plate by the no slip condition is going at velocity v. In just pure Couette flow we have a constant pressure in the x direction, so dp dx is equal to 0, and we get a linear velocity profile between the two plates. So it looks like this. It's not quite the same as a boundary layer, remember, because the boundary conditions at the top are different, although the boundary condition at the bottom of the plate is pretty much the same. Now we also looked at the case of Couette flow where we have a pressure gradient in the positive x direction. So the top plate's still moving at velocity v, the bottom plate's still stationary, and we have a high P on the left and a low pressure on the right, and now we put in the bottom velocity, it's 0, the top velocity again is v, but now we have a parabolic velocity profile between the two that looks something like this. So the velocity vectors moving in that direction. And note we have exactly the same thing as we had for the boundary layer. At the base of the wall we have a steeper velocity profile in the case with a favourable pressure gradient than we did in the case up here with no pressure gradient at all. And then we looked at Couette-Poiseuille flow with an adverse pressure gradient, so a low pressure upstream and a high pressure downstream. And here we found that, well, once again we have, by the no-slip condition, a zero velocity at the bottom, velocity of v at the top, but now we have a parabola going the other direction, which looks something like this. And if I draw in the velocity vectors, we have at the bottom a little region of reverse flow, and that's exactly the same as we have in the boundary layer here. So we've seen this concept before. What I want to talk about next is why this has such profound implications for aerodynamics. So let's consider the flow around a curved surface. And to start with, let's consider inviscid flow. Now, if we consider the front, because it's inviscid flow, we're going to have perfect slip at the bottom, in fact perfect slip throughout, and the velocity profiles might look like that. It's a flat velocity profile. Around the middle we're going to find a slightly higher velocity, simply because the fluid is having to get round the obstacle. So I've drawn that in here. A higher velocity, but again a flat velocity profile because the flow is inviscid, and around the back of the object we'll find the same velocity that we had around the front of the object, if it's symmetric, in the inviscid flow case. And let's look at the pressures. Let's say at the front we have a high pressure. Of course everything's relative, but let's just call that high. Around the middle of the object, where it's going faster, we'll have a low pressure, and then around the back we'll have the same pressure that we had at the front. Call that high. Now, of course, in any practical situation the fluid will have a finite viscosity, and this means that around the boundary we'll get a boundary layer. So let's draw in red the velocity profiles for a viscous fluid, fairly similar in the free stream, but then near the boundary we get a drop off in the velocity. Now note that in going from the front to the middle we're going from a high pressure gradient to a low pressure gradient, so that's a favourable pressure gradient, and we're going to find that the boundary layer gets a little bit steeper. Everything's being accelerated due to the pressure gradient, so we get a slightly steeper boundary layer profile. And of course that means that there'll be no reverse flow around the front of the object. However, around the back we're going from a low pressure to a high pressure. We have here an adverse pressure gradient, and so let's draw on the velocity profile in the boundary layer, where we'll start off the same in the free stream, but then we'll get a little bit of reverse flow at the bottom in the boundary layer. So those are the velocity profiles around the back, and this has very profound implications for the flow. Note in the middle all the fluid in the boundary layer is moving forwards. At the back of the object, some of the fluid at the bottom of the boundary layer is moving back. Now where these two meet we're going to get a mini stagnation point, and the fluid is going to have to move upwards like that. And if we were to draw the boundary layer at that point, we of course would find that it had a velocity profile that looked something like that. Zero velocity just above the wall. Now this completely changes the nature of the flow. The flow is coming around the front of the body, moving past the top, hitting this sort of stagnation point, and then moving up, and it'll bend away. The flow at the back has reversed. And so what we have here is called a separation point, and behind it we have a recirculation region. And all this arises because of the effect of an adverse pressure gradient on the boundary layer. And here's an example of that. This is taken from an album of fluid motion. This is a sphere, a metal sphere that's been coated in condensed milk, of all things, and then placed in a flow from left to right. Now we can see in this picture the sphere. I'll just draw it around the front. It looks something like that. We can see around the front that there's no separation. We've got a favourable pressure gradient. It'll be high pressure here and a low pressure at the shoulder of the sphere, and the boundary layer remains attached. However, around the back we can see quite clearly that around this point here the flow has separated and moved away from the sphere, and if we draw in the streamlines they look something like that, and here we have a region of reverse flow, and this has arisen because the boundary layer has separated. Now there's another important point I want to raise here, which is that this has happened in an entirely laminar flow. Some people confuse separation and turbulence, and there's no reason to do that. We haven't even mentioned turbulence yet in this course, and yet we've got separation. And the separation of a boundary layer is an entirely laminar phenomenon. Now I'll explain briefly why this has such an important impact on aerodynamics by considering what was called D'Alembert's paradox, which is essentially that you can't get any lift in an inviscid flow that is completely irrotational. So let's consider inviscid flow around a cylinder. I'll just highlight two things here. We've got a stagnation point at the front where the flow goes to zero, flow velocity goes to zero, and a stagnation point at the back where the flow velocity goes to zero. And this flow is obviously symmetric, up and down as well as left and right, and because it's symmetric there's no lift on this object. Equally, there's no drag. Underneath I'm going to draw a picture of a wing, and this wing is in the same inviscid flow as before, and again I want to draw your attention to the stagnation point at the front, the stagnation point at the back, but particularly to this region here, where because it's an inviscid flow there can't be any boundary layer separation because there aren't any boundary layers. The flow at the very back, let me draw this as a zoom, the flow at the back whips right round the back without separating and reaches the stagnation point, or the separation point, and then moves away. Sorry, the stagnation point, not the separation point here, which is just a purely inviscid stagnation point. So the flow, because it can't separate, because there are no boundary layers, just moves straight round the back and then hits the stagnation point and moves away. And in fact for this wing, just as for the cylinder, it turns out that there's no lift and again no drag, which is D'Alembert's paradox, because we know that in the real world these things do have lift and they do have drag. So what's the difference? Well, let's look at the cylinder in a viscous flow, which we've just done, and we know that in a viscous flow the flow separates at these 2 points here and we get 2 separation points, and this means that we get a little bit of reverse flow around the back of the cylinder. And in fact what you can do, and you'll do this in the third year, is look at the pressure around the front of the cylinder, the pressure around the back of the cylinder, and from that you'll realize that there is a drag force on the cylinder. In this case of course though, in the viscous case, it's symmetric top to bottom, so in this case there's still no lift. But now let's look at the aerofoil. The flow comes in straight as before. Let's follow the streamline at the bottom. Now this went around the bottom of the aerofoil, and in the inviscid case it would have whipped around the back to the stagnation point and then moved away. In this case though, to whip around like that would involve an enormous adverse pressure gradient, and the boundary layer separates and this bit of fluid moves off like that. The bit on the top now moves around the back and follows it, and you get what's called at the back here the cutter condition, and which essentially says that the flow remains parallel at the tip. And this has arisen because the boundary layer at the tip, at the back of the wing here, can separate, can move away, and let the flow line up as it has done here to give you the cutter condition. Now you can think of why this gives you lift in all sorts of ways. The classical way at school is to say at the top you've got a low pressure underneath, low pressure on top and a high pressure underneath, which gives you lift. Another way is to look at the streamline curvature, which says that because the streamlines are curving all downwards, the pressure at the top must be higher than the pressure just above the wing, which must therefore be lower, whereas underneath it's kind of the other way around. The way they're turning means that the pressure at the bottom here must be lower than the pressure just underneath, which must be higher, and because these two pressures must be the same, because the fluid streamlines all came from the same flow, which was going in the horizontally upstream, it means that you must have a lower pressure on top of the wing than underneath the wing, and therefore you must have lift. Or you can do the crudest way possible, which is the one I actually prefer, which is to say that the fluid came in horizontal, and when it left it was going down. In other words, behind this wing you've got a whole bunch of fluid that's been pushed down, just as you have underneath a helicopter, and that gives it lift.
This drawing, derived from potential flow theory, shows how the streamlines around a combination of a flat plate and a cylinder would look if fluids did not have viscosity. When a real fluid, water, flows around the same shape, the flow is quite different. Boundary layers, thin layers of fluid in which viscosity affects the flow dynamics, are formed along the surfaces of the object. The behavior of these boundary layers under the influence of pressure gradients can, in some cases, drastically alter the flow. This streamline pattern is very nearly what one would predict from inviscid flow theory. Because the Reynolds number is large, influences of viscosity are confined to a narrow region close to the surface of the wing. The primary effect of viscosity is simply to create a drag force on the wing through the integrated effect of surface shear stress. As the angle of attack is increased, viscous effects become more pronounced. Pressure gradients imposed on the boundary layers become more severe, and separation occurs on the upper surface. Now the airfoil is stalled. A region of recirculating flow is formed over the upper surface of the wing. In order to understand how viscous forces can influence the entire flow field, we shall look at what causes boundary layers, how they grow, how they respond to pressure gradients, and the difference in behavior of laminar and turbulent layers. Before attempting to understand the boundary layer flow over this object, we shall look at the flow of a viscous fluid along the flat plate alone. These streamlines of water flowing in a channel are made visible with hydrogen bubbles generated by electrolysis. The flow is uniform and laminar. The fact that the timelines, the vertical patches of bubbles, remain perpendicular to the streamlines shows that the unobstructed flow is free of vorticity. Here is the flow over a plate. The flow is two-dimensional and laminar. Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present. In the narrow boundary layer region adjacent to the plate, the shearing forces and inertia forces are of equal importance in determining the motion of fluid elements. Outside of this region, the shear stress can be neglected. The thickness of the boundary layer increases along the length of the plate. Fluid deceleration is transferred from one fluid layer to another by viscosity. Moving the camera with the free stream velocity will give a better view of the boundary layer growth. The velocity throughout the boundary layer is less than that in the free stream. There is no slip between the plate and the layer of fluid immediately adjacent to it. At the plate, the relative velocity is zero. This is the no-slip boundary condition of viscous flow. The displacement of the bubbles corresponds closely to the velocity profile in the boundary layer. The thickness of a boundary layer is sometimes defined as the distance delta from the surface to where the velocity u reaches some fixed percentage of the free stream value. For our purpose, we will use 95% of the free stream velocity to define the thickness of our boundary layer. The gradient of the velocity normal to the wall, delta u by delta y, times the viscosity mu is the wall skin friction or shear stress tau. The greater the velocity gradient normal to the wall, the greater the shear stress. Upstream, the velocity gradient is fairly large. Downstream, it is much less. This composite photograph compares the two velocity profiles. The smaller gradient downstream indicates the wall shear stress decreases along the plate. The growth of the boundary layer thickness along the plate can be explained by considering the time history of the vorticity within the boundary layer. Stokes' theorem states that the area integral of the vorticity omega, bounded by a closed contour, is equal to the line integral of the velocity around the bounding contour. The circulation gamma is the sum of the vorticity enclosed by the contour. The contour at the upstream station is a unit length along the plate and is more than a boundary layer thickness in height. At the top, the local velocity is parallel to the contour, but in the opposite sense. The components of velocity along the right and left parts of the contour are virtually zero. Because there is no slip, the velocity contribution to the circulation at the surface is in fact zero. Therefore, the circulation is minus the free stream velocity times a unit length. Downstream, the circulation is also equal to minus u0 times the unit length. The total amount of vorticity within each contour is the same. Because there is no vorticity upstream of the plate, and because the circulation per unit length along it is constant, we conclude that all of the vorticity in its length. Upstream, 95% of the total vorticity is contained within this area. Downstream, 95% of the total vorticity is contained within this area. Viscosity acts through the mechanism of molecular diffusion to spread out the vorticity as it is convected downstream. The local boundary layer thickness is a measure of the distance vorticity has diffused away from the plate. We can relate the factors controlling this growth process in the following simplified manner. The diffusion length delta increases as the square root of the product of the kinematic viscosity nu and the time of diffusion t. At a distance L from the leading edge, the diffusion time is proportional to L divided by the free stream velocity u0. We combine so delta over L is proportional to 1 over the square root of the Reynolds number. This relationship is valid only at high Reynolds numbers when delta is small compared to L. Increasing the flow velocity will decrease the boundary layer thickness at any given station along the plate. To see this effect, here is the normal flow.